All right, we're going to look at these problems with L'Hopital's rule. These are pretty straightforward problems. I have another video at the beginning of, this is in a playlist here, and the first video in the playlist just goes through L'Hopital's rule with a very basic example and kind of explains how to use it. So these are just going to be going through pretty quickly 3 problems where we can use it. So this is number from the Stewart textbook, number 14, 15, and 22 from section 4.4. So let's put those down a little bit out of the way. Work on number 14 here first. And first of all, you can only use L'Hopital's rule when you get that indeterminate form, either 0 over 0 or plus or minus infinity over plus or minus infinity. If you get a different kind of indeterminate form, you might need to do something else first to the expression in order to get it into one of those forms. That's for a later video. So if you look further down the playlist, I have at least one example of that at this point. I might add some more in the future, where you have to kind of manipulate things first to get into one of the appropriate forms. These, I think, all should be good to go, though. So, it's tempting here. One thing you don't want to do, don't do this. I just want to be very clear. And if you do it, just make sure you erase it when you're done or cross it out. Don't do this. Don't write equals 0 over 0. Okay, now it is true that when you plug in 0, you're going to get 0 on top and you're going to get 0 on the bottom because cosine of 0 is 1 and 1 minus 1, right? And that is what we want to see, is that indeterminate form of 0 over 0. However, when you write equals 0 over 0, just keep in mind that is undefined. The value of 0 over 0, it has no value. It is undefined. And so if you say that this equals 0 over 0, we're actually saying that this limit is undefined, but it's actually not. We're going to get an answer for this limit. It's going to have a numerical value, and so it can't possibly be equal to 0 over 0, which is undefined. So as written right now, whoops, this is a false statement, and you don't want that. So don't write that. Don't even start by writing that. If you can tell right away that it's 0 over 0, you don't necessarily need to even show that work. If you need to do that work, way off to the side, don't write equals, just kind of plug in, 0, plug in 1 minus cosine 0, 1 minus 1, 0. Okay, you got it, whatever you need to do, but don't connect it to the thing that you're answering, okay? You do, however, have to show something to justify that this is that we can use L'Hopital's rule. So you have 2 choices. You can either write is of the indeterminate form 0 over 0. That justifies using L'Hopital's rule. Or you can, and I don't like to do it that way. I don't like writing a lot of words in a math problem if I can just show it mathematically. So instead, what I like to do is I like to show the 2 limits separately of the numerator and the denominator. So I'm going to just write the limit as x approaches 0 of x squared equals 0, and the limit as x approaches 0 of 1 minus cosine of x. You can show 1 minus 1 if you want. Equals 0 though, right? Equals 1 minus 1 equals 0. And so now what we've shown is that it does give us the 0 over 0, right? But we haven't written equals 0 over 0. And that means now we can use L'Hopital's rule. And I'm just going to go ahead and write. I do like to write by L'Hopital's rule. I'll write that underneath this in a second. Equals the limit as x approaches 0 of, and what you can do now is just take the derivative of the top and the derivative of the bottom and try again. That's how L'Hopital's rule works. So we get 2x. On top, we get the 1 goes away. Derivative of negative cosine of x is actually positive sine of x on the bottom. And now we're ready to try direct substitution again, right? And so I'm going to get this work up out of the way because I'm anticipating we still have the same problem, right? When I plug 0 in on top, I'm going to get 0. When I plug it in on the bottom, sine of 0 is 0. I can see that. And so, it might be tempting to say, oh, no solution. L'Hopital's rule didn't work. First of all, L'Hopital's rule doesn't necessarily always work. So don't just assume that if you get stuck with L'Hopital's rule that the limit does not exist. It does not guarantee that. Okay, L'Hopital's rule is a very helpful, useful tool. It does not always help, though. There are certain circumstances where it doesn't. In this case, it actually does. We're just going to go one more step, right? The fact that we're getting 0 over 0, let me show that. The limit as x approaches 0 of 2x is 0, and the limit as x approaches 0 of sine of x is 0. The fact that we're getting 0 over 0 here means that we can use L'Hopital's rule again. It means that this limit here is equal to the limit as x approaches 0 of the derivative of the numerator over the derivative of the denominator again. So we can do that, and we will. And you can kind of tell it's going to work too, because on top you have 2x. Whoops, let me get rid of that. On top you have 2x now. Remember we had x squared before. 2x, when I take the derivative of that, is just going to be 2. So I can kind of see things clearing up, even if it's not as gone as I wish it were, right? Well, I don't know about you. I'm happy because I like doing this. So I'm good to do it again. Oh, by the way, I do like to write by L'Hopital just to justify my work there. By L'Hopital's rule. Okay, can you abbreviate things? I suppose, but it doesn't take that long to write it out. May as well be err on the side of clarity, right? Especially if you're taking an AP exam on an FRQ, I would err on the side of clarity. You have enough time if you know what you're doing on those problems. So do them right. And again, we're just going to take the derivative on top, derivative on the bottom, and now we're in business. Now we can just plug in 0 for x, and we get a 2 over cosine of 0, which is 1, and the answer is 2. That is the answer to this problem. Again, I'm going to write by L'Hopital's rule one more time here, because we used that again. Okay, better to be thorough than not, especially when a problem says justify. That said, I will say on the AP exam, the most important thing to show is the justification that allows you to use L'Hopital's rule, which is this part over here, right? And so you don't necessarily have to line it up exactly like this, but showing this lets you use L'Hopital's rule. And the most important thing to show if you're justifying is the criteria, especially in the AP exam. But naming the theorem or rule or whatever is always a good idea if you know it, and you should know it. All right, let's do the second one. I'll talk a little less this time. I have a tendency to over-explain in these things. And I did talk about all this stuff in the introductory video to L'Hopital's rule too. All right, here, plug in pi over 2, and maybe check first, just kind of like before. You don't just assume you're going to use L'Hopital's rule, even in a section on L'Hopital's rule. I think number 19 in the section, maybe I'll throw it up at the end. I think number 19 is a red herring, and you don't actually want L'Hopital's rule. Anyway, 1 minus sine of pi over 2. Well, sine of pi over 2, if you think on the unit circle, it's up there. The sine value is 1 up there. So that is going to be 0 on top. And then if you plug in pi over 2 here, 2 times pi over 2 is pi, and the cosine of pi is -1, so 1 minus 1 on the bottom as well. So yes, we are going to use L'Hopital's rule. I don't know, maybe you're tempted to throw like a double angle identity in there. I don't think we need it here. And I will say on the AP exam, they're not making you do that stuff. So I'm not going to bother with it. The limit as theta approaches pi over 2 of 1 minus the sine of theta is 0. And the limit as theta approaches pi over 2 of 1 plus cosine of 2 theta is 0. Show as much work as you feel like you need to. But, if you can, that's easy enough to evaluate, I think. Okay, but justify those answers. Show that work to justify those answers. This is what lets us use L'Hopital's rule. So now I can say this limit equals, by L'Hopital's rule, the limit as theta approaches pi over 2 of, the 1 goes away, derivative of sine is cosine, so I have negative cosine of theta on top, which, that's going to be another 0. I can see it coming, right? They're messing with us. And then on the bottom, the 1 plus, that goes to 0. Cosine of 2 theta. The derivative of cosine is negative sine. So 2 theta. And then times the derivative of the inside, which is just going to be 2, right? So I'm going to go ahead and put that. It's from the chain rule, right? So the outer function there is cosine, derivative is negative sine. Keep the inside the same. Multiply by the derivative of the inside. Derivative of 2 theta with respect to theta is just 2. So I'm going to rewrite this. And by the good lesson here too, When you are working on limits and you do like L'Hopital's rule, you can still mess with this the same way that you can mess with anything in any limit, right? So like do things that make it easier. If there's simplifications, if there's something on top that then can be moved to the bottom with like a negative exponent or something and clean it up a little bit, absolutely do it. Reduce common factors, like all of that stuff. Anything that makes it easier, you can still do it. We have not evaluated the limit yet, obviously, so you want to keep the limit notation until we do it, until we actually like plug in and get an answer. The negatives cancel out, so I just have cosine of theta over 2 sine of 2 theta. And again, I can see that, when I plug pi over 2 in for theta on the bottom, 2 pi over 2 is pi again, and that's the sign there is 0. So this problem was designed for L'Hopital's rule twice again. Oh, by the way, I didn't label that. You could write by L'Hopital's rule right up here, or you could kind of write it below. L'Hopital's. Okay, and now I'm going to show that I can use L'Hopital's rule again. So again, this was just kind of for that work up there. The limit as theta approaches pi over 2 of cosine of theta is 0. The limit as theta approaches pi over 2 of 2 sine 2 theta is 0 because the sine of pi is 0. And so this is my justification for using L'Hopital's rule a second time. So equals, again, by L'Hopital's rule. The limit as theta approaches pi over 2 of, on top we're going to get derivative cosine, negative sine of theta. On the bottom, 2 sine of 2 theta. The derivative of sine of 2 theta is going to be, cosine, right? So we still have that 2, and then times the cosine of 2 theta, and then times another 2 because of the chain rule again, right? And so it's actually 4 cosine of 2 theta on the bottom there. If you want to rewrite it, you can. But at this point, I feel comfortable just plugging this in. So I have on top, I have -1 because the sine of pi over 2 is 1. And I have that negative already. And then on the bottom, I have 4 times the cosine of pi, which is -1. And so the negatives cancel out. I actually get 1/4. And that's my answer. That is the value of this limit. This one up here was 2. When there's a lot of work, sometimes it's nice to kind of circle your answer, show what you're getting. Maybe restate the question even again, like say this limit equals 1/4. Just make it really clear, especially again on the AP exam, you've got 108 points to work with, and you're trying to earn as many as you can. And the margins are like a point could be the difference, right? A point could be the difference between a 4 and a 5, or a 3 and a 4, or 2 and a 3. And if you have the time, and how long does it take to circle something? Just make sure that they're seeing your answers, especially if your work kind of moves around the page a little bit. Try to get a flow to it. Try to make it clear, how your work works. Mine gets a little, especially when I'm trying to fit things on one slide here like this. But try to have a nice clean flow to your work, and definitely make sure that the answer to the question is clear. And it never hurts to go back and just look at the question again. When you think you're done, make sure that you actually answered what was asked. Anyway, all right, this next one. Again, L'Hopital's rule looks like, because again, if you plug in 0, that's 1. That's 1. 1 minus 1 is 0. And then on the bottom, I get 0. So kind of verify that for myself. And then I'm going to write, again, the limits separately, because now that I know I'm using L'Hopital's rule, then I know I'm going to have to write this out anyway. So I will just do it. 8 to the t minus 5 to the t. If you want to show a little work, you can be like equals 1 minus 1 equals 0. Or if you're comfortable just writing equals 0, that's cool. And then the limit, at least it's cool with me. I don't know, maybe not all teachers feel that way. So I've shown the limits for the numerator and the denominator, and they're both 0, and that means I can use L'Hopital's rule. And so let's do it. Equals the limit as t approaches 0 of, on top, The derivative of an exponential that does not have base e, if you don't know it and you want to review it, it's just that exponential. So in this case, like 8 to the t, the derivative will be 8 to the t, and then times a natural log of 8. It comes from a chain rule because of the way that you can write 8 to the t as like e to the natural log of 8 to the times t. Anyway, something to review if you need to, but here's the derivative. Natural log of 8 times 8 to the t. And then same thing with the 5 to the t. So minus natural log of 5 times 5 to the t. You just got to know all those derivative rules. On the bottom, the derivative is just 1. And so, hey, this was a one-time deal, right? Now we can plug in 0, we get an answer, and we got natural log of 8 times 1 minus the natural log of 5 times 1 divided by 1. And so that's it, natural log of 8 minus natural log of 5, or if you're fancy, the natural log of 8/5 using properties of logarithms, right? I don't like the way that looks. Let me fix that 5. It's still not that good. There we go. All right, and one more thing, because I didn't write it this time, by L'Hopital's rule. And that's it. All right, I think I'm going to go ahead and stop this video. I will make one more in a second here doing that. I think it was number 19. I'm going to double check where you don't actually need L'Hopital's rule, but it kind of looks like you might. So check that one out if you want to see.